Hi, this is Mr. Ferguson, and I'm here to introduce the final video for Unit 6, Covalent Bonding, and we're going to combine Lesson 6.6 and 6.7 in this lesson together because they kind of go together. We're going to talk about VSEPR Theory and molecular geometry in the lesson. So the goals would be to explain the main idea of VSEPR Theory, and then to use VSEPR theory to predict the shape of simple covalently bonded molecules, and to distinguish between the molecular geometry for a molecule and the electron geometry of the molecule, and hopefully be able to identify both of those for a simple covalent molecule or of a simple covalent compound. So let's get to it.
So first we're going to start off with the definition of the Vesper Theory. The actual acronym here means valence, shell, electron, pair, repulsion. That is something you should know. And basically what it means is that when we have the electrons grouping around a central atom, they will repel from one another in a way that they'll be as far away from each other as possible. It's like trying to hold magnets next to each other. They're going to push each other away to the lowest energy states possible, and electrons are no different. So once they get the farthest away, they are happy and they'll take up some type of geometry. And these electrons groupings equal any lone pair or any groups of electrons involved in a single, double, or triple covalent bond.
So for the purposes of Vesper theory, we don't treat a single bond any differently than a double or triple bond. They're all considered an electron grouping, as is a lone pair.
Which changes the geometry. We're going to have lots of practice with the geometry in class, so let's move on. So our first geometry we're going to look at here is carbon dioxide. If you notice, there's the Lewis structure drawn, so if you have yet to learn to do those, you should probably take some time and relook over how to do them because you need them for this. And you can see it's drawn out pretty straight, but when you put the molecular ball and stick model together, you can see that there's a central atom, and then the two oxygens are indeed linear from it, or straight out from it.
And there's two electron groupings. There's the electron grouping in this double bond and this one. And in that configuration, the farthest they can get away from each other is to be on exactly opposite sides. So how we express that is if you kind of consider this like the apex of an angle, and you draw a line to the center of that atom and that atom, what is the angle
between
that you get? Two. That's called the bond angle. So and just like in geometry class,
obviously 180 degrees, being as they are as far apart as they can be. And then the electron geometry is the geometry of the electrons counting the lone pairs of the central atom. But since there are no lone pairs around the central atom, in this case, the electron geometry and the molecular geometry are the same, and this one's the easiest one. It's known as linear. So this is a linear electron geometry and a linear molecular geometry. Remember, they will change and be different as we move on.
So that's what we would expect anytime you have a central atom with only two electron groupings.
Yeah. Okay, next slide.
So now we're going to move on. We're going to talk about an electron, or the geometry we get when we have a central atom that has three electron groupings. And this is a little bit of an odd circumstance. It doesn't happen very often, but the element boron will do that. Boron is what we would call an octet rule exception.
It's a hextet rule in this case.
And is boron stable with 6 electrons? It only has those 3 valence electrons, and so it likes to bond up and share 3 pairs, and that's stable for it. So there's our Lewis structure. Okay, boron trichloride.
And next to it, of course, is our ball and stick figure. And once again, you have to figure out the angle between these atoms, and being as there are 3 of them distributed evenly over 360 degrees, you take 360 divided by 3 and get 120 degrees. And the electron geometry on this one is known as
trigonal planar.
Yep, and the molecular geometry is the same, trigonal planar, because it's flat and it looks like a triangle.
So you'll notice, we keep distinguishing between these, but yet they're the same. That's because we haven't looked at any examples yet where there's lone pairs.
Exactly. There's a whole list of these. I think there's about 12 shapes in all if you start tearing them apart. But we'll take a look at them in class if we don't cover them here. So the next one we're going to look at is formaldehyde. You can already see we have the Lewis structure drawn over here. There's a double bond between the carbon and the oxygen, and then there's the two hydrogens, and that's giving us a grouping of 3 bodies around the central atom. Even though there is a double bond, the carbon only has 3 things attached to it. So much like boron trichloride, you do still get that trigonal planar geometries for both of them, both electron and for molecular. So then this one would still be trigonal planar. Just because there's a double or triple bond present doesn't mean it can't be trigonal planar.
Okay.
Next. So our next one here is a central atom with 4 electron groupings around it. Once again, there's the Lewis structure of it.
That would be methane.
And then here are the ball and stick models, and it already gave us the bond angle between it. Since there are now 4 bodies, they repel each other outside of a flat plane, and 109.5 is the most distance that they can put between each of them.
If it was flat, it would be 90, but we have to remember it's 3-dimensional, and so they can actually increase the bond angle by
going out of
twisting a little bit.
Yeah, going out of the plane. So 90 is less than 109.5. So
and this we see a lot with carbon. It's got these 4 things at 109.5 degree bond angle. And what's the name of that geometry,
this
Mr.
one would be
Hunter?
your tetrahedral. Tetra, of course, being 4, and hedral, just giving it its shape. So it's a 4-sided object or 4-atomed object. So there we have it.
Okay, and again, this is still we have the same. The electron groupings are matching the geometry of the molecule because they're all
present.
All attached.
We will
to
give you
atoms.
some examples of ones that they're not.
Well, yeah, the next one we're going to see a place where they're not the same anymore.
All right. So here's the example for the one that are no longer the same electron and molecular geometries. This is ammonia, NH3. If you notice, in the center there's nitrogen with 3 hydrogens around it, and then a lone pair. This is the first time we've had one with a lone pair on it. Okay. So the bond angle, since there are 4 objects around the central...
This is an electron grouping as well as the bonds.
And it does count as an object around the center. So the bond angle would still be 109.5. I think in reality it goes to like 112
107 or something, I think. But it's close to that. And so what's not shown in the molecule here is there's this lone pair
drawn off
projecting up off the top there.
So now the electron geometry, there are 4 things around it. So the electron geometry would still be tetrahedral. So the electron geometry is tetrahedral, but the molecular geometry changes because there are only 3 atoms around the center. And I believe this one's called trigonal pyramidal.
Right, and so you can see it kind of looks like a triangle-shaped pyramid, so the name kind of fits. So as soon as we introduce those lone pairs, now we're not going to have identical electron geometry and molecular geometry.
You're going to have a whole chart that goes over every single possible combination. I think it's a nice graphic that we allow you to use.
And we have some really nice simulations we can do on the computer where you can build the molecule yourself, rotate it around, look at the geometry, see how adding lone pairs affects geometry and all that kind of thing.
Okay, I think we've got a few more examples for you then. Here's another one. This is water, H2O. Again, central atom is O in this case, with 2 hydrogens coming off of it. But now you can also see there are 2 sets of lone pairs. And here's the ball and stick. So again, the bond angle for this one, being as it's a 4-body entity, would be 109.5.
Because again, even though there's only 3 atoms, we have 2 separate lone pair electron groupings projecting up, but that we don't show in the ball and stick model, but they definitely affect the geometry because they're still repelling those bonded electrons away from them.
So the electron geometry in this case would still be tetrahedral because there are 4 bodies around the center. But now the molecular geometry turns into something known as a bent geometry. And pretty much any time you have two atoms attached to a central atom with any type of number of lone pairs, it is going to be considered a bent molecule because it's not going to be planar anymore. All right, I believe we have one more example for you. So here is just basically a summarizing slide of the three different shapes that the tetrahedral can undergo. There's the first one that has 4 atoms around it, like methane, and it is a full molecular tetrahedral and an electronic tetrahedral. But then we went on to ammonia that had the 3 atoms around it with 1 lone pair. It's still a tetrahedral family, but its subgroup would be that trigonal pyramidal. And then
so the molecule is this, but the electron geometry is still the tetrahedral.
Exactly. And then lastly, we have water. Water has 2 atoms around it and 2 lone pairs. So it still belongs to the tetrahedral family, but its molecular shape is that of bent, because if you were to look at it, you would see the 2 atoms of water, but you can't see lone pairs, I guess, in the...
No, they never show them almost never on the ball and stick models. There's some that will include it, but this is the shapes we've covered here is the ones that we would have you being totally responsible for a test. We're going to cover some of the more exotic shapes like trigonal bipyramidal and octahedral and seesaws and
but that'll be
T-shape.
a whole different lesson, maybe. All right, have a good night.